Once upon a time, in a deep, deep realm of the sea, there was a little creature living all alone in the dark where no sunlight ever reaches. This creature is Vampyrotoides infernalis, also known as vampire squid, the last member of the long and forgotten dynasty of vampyromorpha. When we think of vampires, we have creatures like him or him in mind. But this creature here is not the common vampire that we are used to find in every tale and story. So why is he called vampire? Having a closer look, we can easily find many similarities between these two kinds of vampires. First of all vampires are known to live in the dark. One is living during night, the other one lives in the aquatic zone in the deep, deep ocean, where dark is always present. Normally, the vampire squid is found between 600 and 800 meters deep, in particular in tropical and temperate waters. But let's explore the adaptations of this animal that make him able to live in this environment. The first one is the cryptical coloration. Indeed, the vampire squid is dark red, and this allows to reduce its visibility to predators. Common vampires shine when exposed to sunlight. Our little friend is also able to shine, but in a unique and particular way. It has the power to shine like a diamond in the total darkness. This phenomenon is known as bioluminescence. Bioluminescence is a very common characteristic at this depth. But how does this process work? How is the vampire squid able to produce light? Bioluminescence in vampire squids is made possible by a molecule called cholinesterase, a subclass of luciferin. Cholinesterase acts as a substrate for the bioluminescence reaction. The renilla luciferase enzyme catalyzes the oxidation of this molecule, allowing the production of cholinesterase and CO2, and emitting blue light with a wavelength of 460 to 466 nanometers during the reaction. This reaction occurs in different areas of its body. The light-emitting organs of vampire squids are the fin-based photophores, the composite organ located behind the eyes, and the epidermal organ scattered over the animal surface, except for the web. The vampire squid has also bioluminescent organs in the tips of all the 8 arms, where they can produce light when stimulated by mild contact. Moreover, the animal is able to release a viscous fluid containing microscopic luminous particles, forming a glowing cloud around its body. This might be a defense mechanism from predators. Another similarity between real vampires and our little friend is that both require oxygen to breathe. While one is breathing air rich in oxygen, the other one typically inhabits the oxygen minimum zone, where the concentration of dissolved oxygen is less than 0.5 milliliter per liter of water. How is it possible for the vampire squid to survive in these conditions? Firstly, it tends to suppress its aerobic metabolism, resulting in the lowest metabolic rate measured for any cephalopod. Due to the low oxygen availability in the environment, it has also evolved specific adaptations to improve oxygen usage. The main one is the presence of hemocyanin as a respiratory pigment in its blood, which has a high affinity for oxygen even at low oxygen partial pressures. Moreover, the absorption of oxygen may be increased by the countercurrent blood flow in the gills, in which the blood and the water flow moves in opposite directions. At the level of the tissue, in other cephalopods, there is the release of O2 due to the Bohr effect. Changes in pH influence the oxygen binding activity of respiratory pigments. So when pH of the blood gets more acidic due to an increase of CO2 partial pressure, the pigment's affinity for oxygen gets reduced so they can release more of it, meeting the tissue's demands. In this case, the Bohr effect is reduced. At the level of the tissues, due to the high cooperativity of the vampire squid's hemocyanin, this respiratory pigment can release oxygen at a lower rate as the hemocyanin is less sensitive to changes in pH and CO2. Another difference that we can find between the common representation of a vampire and the vampire squid is related to locomotion. Indeed, Edward Cullen is able to jump and run really fast. Instead, this animal conducts a passive lifestyle, has a neutral buoyancy to reduce the energy expenditure, and even its muscular tissues are reduced. Their typical way of moving is called bell swim, as they use the web between the tentacles to perform a movement similar to the one made by jellyfish, which requires little oxygen. Another difference regards the feeding. Common vampires feed on animals' blood, and they can clearly be defined as active predators. Instead, the vampire squid is not an active predator. It is in fact primarily a detritivore, and feeds on detritus of various sizes that constitute the marine snow aggregates, including the crustacean remains, such as copperpills, gelatinous zooplankton, discarded larvation houses, radiolarians, diatoms, and facial pellets. These aggregates have a high nutritional value and in particular a great organic carbon content. To detect and capture this detrital matter, it uses its multifunctional filament characterized by the presence of muscle cells on one side and sensory cells on the other. The vampire squid extends this long filament and waits. When a piece of detritus touches it, it gets slowly retracted towards the mouth region, and the food particles get encapsulated in a mucous ball and transported by some serum to the mouth. This particular feeding method allows this organism to reduce even more its oxygen and energy requirements. The filament can also be useful to detect the presence of predators. And while we talk, our little friend continues its life in the deep sea, facing 1,000 adversities with its super adaptations happily ever after.